Hello everyone, welcome to this KTHM e-learning channel. In this lecture, we are going to discuss gradient of scalar function in curvilinear coordinate system. Let us start. In this lecture and in the next lecture, we are going to learn these three operations. That is this del. Del is a vector differential operator. When this vector differential operator operates on scalar function, here psi is a scalar function. When this vector differential operator operates on scalar function, then the resultant is a vector. Then the second operation in next lecture, that divergence. In this vector, if we take the dot product of this vector differential operator with a vector function, then the resultant is a scalar. Therefore, this is also called scalar product, a divergence. And the third operation which we have to study is a curl. When we take cross product of this vector differential operator with vector function a bar, then the resultant is a vector. So it is called vector product. These three operations which we are going to study one by one. The first one is gradient. Gradient in orthogonal curvilinear coordinate system. What is gradient? The gradient of a scalar function psi. Here psi is a scalar function of the coordinates, general coordinate u1, u2, u3. Then it is denoted by del psi. This del is a vector differential operator and psi is a scalar function, and this del psi is a gradient, or it may be denoted by this vector bar, that del bar psi, where del is a vector differential operator. It is also the notation grad psi is also used to represent gradient. This grad psi is also used to represent the gradient. Then what is gradient? The gradient of scalar valued differential function psi of several variable is a vector field. That is, when this del operator operates on psi, scalar function psi, then the resultant is a vector field. Resultant is a vector field. Then what gradient represents, or what is the physical significance of gradient? The gradient of vector, the gradient vector gives the direction and the rate of fastest increase. Use the rate of fastest increase of scalar function and the direction of increase. The direction of the gradient is the direction in which the function increases most quickly or most rapidly from point P, and the magnitude of the gradient is the rate of increase in that direction. Therefore, magnitude gives rate of increase and direction gives the direction of increase. This we see in detail with two examples. The first example, consider a scalar function temperature. Temperature is a scalar function. Then at any point P having coordinate u1, u2, u3. This is a point P represented by this coordinate u1, u2, u3 around the source of temperature. Let this is the source of temperature. Then around the source of temperature, near the source the temperature is high, and as we go away from the source, temperature decreases. Let at point P the temperature is T. Then T is also function of the coordinate. As the position of the point P changes, the value of T changes. Therefore, T is function of coordinate. Then the gradient of T. Then gradient of T that point, at that point will show the direction in which the temperature rises most quickly, and the magnitude of gradient will determine how fast the temperature rise in that direction. Here this point P, then towards the source, this is the direction in which there is a maximum rise in temperature. This is the direction in which the maximum rise in temperature, and the change in temperature, that the magnitude of the gradient. If you draw a spherical path, if you draw a sphere at same with constant radius, then all points on the surface of the sphere, all points on the surface of the sphere have same value of t, same value of t, but the direction is toward the source. That if the point is here, then direction, this is the direction. So the magnitude is same, but direction varies from point to point. Therefore, the gradient gives magnitude as well as direction. If we draw another sphere, then the difference of temperature and the distance, the ratio of this difference of temperature, the difference of temperature per unit distance, that is the gradient. Then take another example. Let this plus q charge is a charge q. Then the charge q produce electric field around it. Then consider a sphere of radius r and let v1 is a potential, because potential is a scalar quantity, scalar function. Potential is scalar function. And on the surface of the sphere, let v1 is a potential. Then draw another surface with radius r plus dr. Let the potential on the surface of the sphere is v2. Then the difference of potential is v2 minus v1. Then this is the change. v2 minus v1 is a change in potential over a distance dr, over the distance dr, and this is the direction electric. This is the direction of the electric. That electric field vector E is equal to minus del V. This is a gradient of V is a scalar function, and this negative gradient of V. This negative sign because along the direction of this electric field the potential decreases. This direction the potential decreases. Therefore this minus del V. Let us derive the expression for gradient. Consider a function psi, which is a continuous scalar. Consider this continuous scalar function psi of coordinates u1, u2, u3. Then del psi is a vector function. Thus we have seen this gradient of psi scalar function is a resultant is a vector. Therefore del psi is a vector function. So let us consider this del psi is equal to f1 e1 cap, f2 e2 cap, f3 e3 cap. Here we have to obtain f1 in terms of u1, u2, u3, f2 in terms of u1, u2, u3, f3 in terms of u1, u2, u3. For this, let uh, position vector r bar is function of u1, u2, u3. Then differential of this r bar, that dr bar is equal to displacement vector dr bar is equal to deva r bar by deva u1 into du1 plus deva r bar by deva u2 into du2, deva r bar by deva u3 into du3. As we have already obtained this expression in previous lecture, that deva r bar by deva u1, the derivative of partial derivative of r bar with respect to u1 coordinate is equal to h1 e1 cap, where h1 is a scalar factor and e1 cap is the unit vector tangent to the u1 curve. Deva r bar by deva u2 is equal to h2 e2 cap. E2 cap is a unit vector which is tangent to u2 curve. Deva r bar by deva u3 is equal to h3 e3 cap, where this e3 cap is a unit vector tangent to u3 curve. This we have already obtained in previous lecture. Substitute this. Deva r bar by deva u1 is equal to h1 u e1 cap. Deva r bar by deva u2 is equal to h2 e2 cap. Deva r bar by deva u3 is equal to h3 3 cap. Then we get dr bar is equal to h1 e1 cap du plus h2 e2 cap du2 plus h3 e3 cap du3 by the property of gradient. This is the property of gradient, that this d psi is equal to a small change in the scalar function psi is product of these two vectors, dot product of two this vector. This del psi is one vector and this dr bar is another vector. That d psi is equal to the change in scalar function is equal to the del psi dot dr bar. But del psi is equal to this and dr bar is equal to this. Substitute this value. Del psi is equal to this and dr bar is equal to this. Then we get del psi is equal to this expression. If we solve this dot product, then e1 cap dot e1 cap is equal to 1. 1 cap dot e2 cap is equal to 0. 1 cap dot e3 cap is equal to 0. 2 cap dot E1 cap is equal to 0, 2 cap dot E2 cap is equal to 1, 2 cap dot E3 cap is equal to 0, E3 cap dot E1 cap is equal to 0, 3 cap dot E2 cap is equal to 0, and E3 cap dot E3 cap is equal to 1. Therefore, out of 9 terms, after simplification we get 9 terms. Out of 9 terms, 6 terms 0, and only we get F1, H1 du1, F2, H2 du2 second term, and third term is F3, H3 du3. That is d psi is equal to, that small change in this scalar function psi is equal to F1 H1 du1 plus F2 H2 du2 plus F3 H3 du3. But by the definition of partial derivatives, this d psi is equal to, small change in scalar function d psi is equal to delta psi, but because psi is function of u1, u2, u3. Therefore, d psi is equal to delta psi by delta u1 into du1 plus delta psi by delta u2 into du2 plus delta psi by delta u3 into du3. We compare these two expressions. Let us compare these two equations. Then delta psi by delta u1 is equal to f1 h1, delta psi by delta u2 is equal to f2 h2, coefficient of d1, coefficient of du2. Delta psi by delta u3 is equal to f3 h3. Therefore, comparing the above two equation, we get f1 is equal to 1 upon h1 delta psi by delta u1. This way we get first value. f1 is equal to 1 upon h1 delta psi by delta u1. f2 is equal to 1 upon h2 delta psi by delta u2. 3 is equal to 1 upon h3 delta psi by delta u3. This way we get values of f1, f2, f3. Substitute these values of f1, f2, f3 this equation. This initially we have considered del psi is equal to f1 e1 cap, f2 e2 cap plus f3. Substitute f1, f2 and f3 in this expression. Then we get this gradient of psi. This del psi is equal to, or simply called gradient, is equal to 1 cap upon h1 delta psi by delta u1 plus e2 cap upon h2 delta psi by delta u2 plus e3 cap upon h3 delta psi by delta u3. This is the expression for gradient of scalar in general curvilinear coordinate system. This is the expression for gradient of scalar psi in general orthogonal curvilinear coordinate system, and where the del operator is this gradient operator, or del operator is equal to 1 cap upon h1 delta by delta u1 plus e2 cap upon h2 delta by delta u2 and e3 cap upon h3 delta by delta u3. Let us obtain gradient in Cartesian coordinate system. In Cartesian coordinate system, the three coordinates are x, y, z. Therefore, u1 is equal to x, u2 is equal to y, u3 is equal to z. And the three unit vectors are I cap, j cap, and k cap. Therefore, e1 cap is equal to I cap, e2 cap is equal to j cap, and e3 cap is equal to k cap. And the three scale factors, h1 is equal to 1, h2 is equal to 1, h3 is equal to 1. If we substitute these values in the expression which just derived, that e1 cap is equal to I cap, e2 cap is equal to j cap, e3 cap is equal to k cap. h1 is equal to 1, h2 is equal to 1, h3 is equal to 1. u1 is equal to x, u2 is equal to y, and u3 is equal to z. Then we get del psi is equal to, that gradient of psi is equal to I cap delta psi by delta x plus j cap delta psi by delta y plus k cap delta psi by delta z. This is the expression of gradient in Cartesian coordinate system. Then let us derive gradient in spherical polar coordinate system. In spherical polar coordinate system, the three coordinates used are r, theta, phi. Therefore, u1 is equal to r, u2 is equal to theta, u3 is equal to phi. P unit vector er cap, e theta cap, e phi cap. And the three scale factors, h1 is equal to 1, h2 is equal to 1, h3 is equal to r sine theta. Then substitute this value in this expression. That E1 is equal to ER cap, E2 is equal to E theta cap, E3 cap is equal to E phi cap. H1 is equal to 1, H2 is equal to R, H3 is equal to R sin theta. 1 is equal to R, U equal to theta, and U3 is equal to phi. Then we get this expression. This is the expression for gradient in spherical polar coordinate system. Then let us derive the expression for gradient in cylindrical coordinate system. In cylindrical coordinate system, the coordinates are rho, phi, z. So U1 is equal to rho, U2 is equal to phi, and U3 is equal to z. And the three unit vectors, 0 cap, E phi cap, and Ez cap. For E1 cap is equal to 0 cap, 2 cap is equal to E phi cap, and cap is equal to Z cap. And the three scale factor H1 is equal to 1, H2 is equal to rho, H3 is equal to 1. We substitute this value in general expression of gradient, then we get del psi is equal to 0 cap dabba psi by dabba rho, E phi cap upon rho dabba psi by dabba phi, plus Ez cap dabba psi by dabba z. This is expression for gradient in the coordinate system. In the gradient in general curvilinear coordinate system, this expression we have obtained. If psi is function of u1 only, psi is equal to u1 only. This function psi is changing only along u1 curve. That is psi is function of u1 only. Then substitute in this expression psi is equal to u1. Then we get del u1 is equal to this expression. But derivative of dabba u1 by dabba u1 is 1. Dabba u1 by dabba u2 0. Dabba u1 by dabba u3 0. These two terms become 0. This becomes 1. Therefore, we get del u1 is equal to 1 cap of h1. If we take psi function of u2 only, then this term becomes 0. This term becomes 0. And this is 1. Dabba u2 by dabba u2 1. Then we get del u2 is equal to u2 cap of h3, h2. And if psi is function of u3 only, if we substitute psi here u3, here u3, instead of psi, if we substitute u3, then this term becomes 0, this term becomes 0, and dabba u3 by dabba u3 becomes 1. Then we get del u3 equal to e cap of h3. These terms we require while deriving the expression of divergence. This we require in next lecture. That's all in this lecture. Thank you.